Humans, without a doubt the smartest animal on Earth. Yet we're unmistakably tied to our ape origins. Millions of years ago, we were apes living ape lives in Africa. So how did we get from that to this? What happened? What set us on the path to humanity? The questions are huge, but at last, there are answers. More than 6 million years ago, we took that first step to separate from the apes.
We see the launching of the career that ultimately led to Homo sapiens.
And 3 million years ago, we see the roots of our big brain begin to take hold in a tiny creature, more like a chimp than a human.
The frontier of human evolution is really being brought to this razor-sharp edge.
And we now know that for millions of years, many different human-like species lived together on the planet, until one day, there was only us. Homo sapiens, the most complex, adaptable animal on Earth. So how did we get this way, and why? A radical new theory reveals how episodes of cataclysmic change forced our ancestors to adapt or die.
I think we should actually look to our proud ancestry and how we evolved in East Africa and say, that's how we survived that, we can survive the future.
So get ready for a ride through millions of years of our history. It's the story of becoming human. Our story, right now, on Nova. Millions of years ago, on the plains of Africa, a momentous event took place. Apes that had walked on 4 legs stood up and walked on 2. Eventually, this change in posture would be followed by a change in their brains. Somehow, over time, they would become us. We know it happened, but we've never known when or why. Until now. In the Sahara Desert, a 6-million-year-old fossil called Tumai may hold the secret of how we first walked upright.
We are writing the first chapter of human evolution. We are very close to the beginning, very close.
And the fossilized bones of a child from 3.5 million years ago hint to us about the beginnings of human thought. We're discovering how many different human species lived on Earth at the same time, and why all but one died out. We, Homo sapiens, are the first ever to be alone. So what powered our evolution? Why did we become human? Scientists are scouring the most remote parts of Africa for clues. The search for answers begins here, in the Afar, northeastern Ethiopia. It's part of the Great Rift Valley, a deep cut in the earth where geologic forces are ripping Africa apart. Millions of years of history are brought to the surface in layers of exposed rock. It's hot and desolate. Dangerous, too. Ancient rivalries and modern weapons have turned the Afar into a no-man's land of simmering conflict. But Zerai Alemzaget has made this forbidding place his life's work. He's searching for the fossilized traces of our earliest human ancestors. The fossil bones of animals like antelopes, elephants, and pigs are abundant. But the fossils of our ancestors are extremely rare. Then, in a stroke of luck, Zerai makes the find of a lifetime. A find that illuminates our origins in a unique way.
On that afternoon, we decided to survey this hillside. And the first thing that was spotted was a cheekbone of the face.
It was a face so tiny, it had to be a baby. But not a baby chimp. He could tell that from its shape. The skull was embedded in sandstone, but as Zerai turned it over, he could see more bones inside.
Everything was squashed against the base of the skull and completely covered by sandstone block.
Clues to the age of the fossil came from a distinctive feature in the landscape. White bands of volcanic ash.
And that is the volcanic ash dated to 3.4 million years ago.
If the volcanic ash is 3.4 million years old, Zerai's fossil, which was lying just above it, must be younger. It was a child from the dawn of human evolution, about 3.3 million years ago. Zerai called the baby Salam, the Ethiopian word for peace. Then he set off on a quest to unravel her many mysteries. Her journey began a very, very long time ago. Imagine the entire span of recorded human history, taking us back to the Egyptian pyramids, about 5,000 years. Double it, 10,000 years ago, when plants were domesticated and agriculture begins. Double it again, to the time when Ice Age hunters paint stunning images on cave walls. And keep doubling, 6 more times, taking us back 1.3 million years, when the first creature who really looked like us hunted on the plains of Africa. And then keep traveling back another 2 million years, and only then do we arrive in the time when Salam lived in Ethiopia, nearly 3.5 million years ago. What were Salam and her family like? What kind of world did they live in? The answers are hidden in their fossil bones. Addis Ababa, Ethiopia. Zerai's home. He's one of a whole new generation of African scientists trying to unravel the mysteries of human origins. Zerai has brought his precious fossil here to the National Museum. His challenge is to release her from the tomb of sandstone in which her bones are encased. He quickly identifies her. She's from a species considered by most scientists to be an ancient ancestor. Australopithecus afarensis, a small chimp-like creature who walked on 2 legs. This is the same species as the famous Lucy, discovered in the 1970s by Don Johanson.
Lucy was terribly important because she was really an amalgam and of different characteristics of ape and human.
I think specimens like Salam and Lucy are extraordinary simply because you can look at them and see evolution in the making.
But seeing evolution in the making will take some work. Salam's fossilized bones are solid rock, held together by a mesh of soft sandstone. it has to be painstakingly removed.
He spent hours and hours and days and years, and then removes the sand grains, grain by grain, working every day.
He's been at it for 8 long years, but the payoff has been amazing. As the work progressed, Zerai revealed an almost complete skull. And tucked beneath it was nearly her entire spine, along with both shoulder blades. Other bones were found nearby.
An almost complete foot. This is the kneecap. The tibia here.
Never before had a child's skeleton been found so ancient and so complete. Her bones would fit in a shoebox, but they speak volumes about her life. For example, to find out how old she was when she died, Zerai looked at her teeth, but not the baby teeth visible in her jaw. The adult teeth growing inside the bone, as seen in a CT scan. From that, we know Salam died at age 3. Like Lucy, she testifies to a crucial step in our evolution. Unlike apes, these creatures walked upright, as the first fossil Don Johansen found clearly revealed.
It was sticking out of the ground like that. And I gently tapped it with my sneaker, and this is what fell out of the ground. And it is this is the top end of your shin bone. So the kneecap would sit right in here. And very close by, in 2 pieces, I found this bone. And when you put them together, and you see how they move and articulate, that it has all the hallmarks of an upright person.
Other bones confirm that Lucy walked on 2 legs, like us.
This is Lucy's pelvis, and you can see how different a chimpanzee is, and the reorientation of these hip bones. In a chimp, they're facing straight forward. So this is what everybody's sitting on in their living room right now. So they're not identical, but clearly these 2 resemble each other much more closely, right, than either one of these resembles the pelvis of an ape.
From the waist down, Lucy was like us. From the waist up, she and her kind were all ape. Salam's skeleton is the same, with chimp-like shoulder blades giving her the range of motion needed for climbing and swinging. These ancient creatures must have spent time in the trees, possibly sleeping there at night to keep away from predators, but walking upright on the ground during the day. They were at home in 2 worlds. What was their environment like? It must have been very different from the Great Rift Valley of today. Across the border in Kenya is one of the hottest and most barren places on Earth. A vast expanse of volcanic rock and burning desert. That's how it is now. But there's good evidence that for most of its history, it was very different. Researchers braving temperatures over 100 degrees are seeing signs of a dramatic transformation here in the Suguta Valley.
The Suguta Valley was entirely covered in water, up to an elevation of about 580 meters.
So you can imagine that all this valley was filled by a huge lake.
A huge lake that's deeper than any of the Great Lakes. In fact, the entire African continent used to be a lot wetter than it is today. Many millions of years ago, Long before Salam and Lucy, Africa was a wet tropical environment covered with rainforest. This is where the ancestors of Salam and Lucy lived. They probably looked a lot like chimps. But then Africa started to gradually dry out. The rainforest began to shrink. By Salam's time, 3 to 4 million years ago, the Great Rift Valley was a mosaic of different environments. We know that from the fossils of the animals that lived here. Their bones litter the ground.
This is a canine of a hippopotamus. So this is probably a skeleton of a hippopotamus. How can one find a hippo in this type of environment? Really nice antelope.
The fossils tell the story of a vanished landscape.
This is a lower jaw of an antelope.
3 million years ago, the Rift Valley was a patchwork of grassy plains, scattered woodlands, lakes, and rivers.
Definitely very different from what we see here today. Wow, a nice pig here.
As their environment changed, scientists believe our ancestors changed too. They had been creatures who spent most of their time in trees, like chimps and orangutans today. But as their forests shrank, some of them developed the trait that we take for granted: bipedalism, walking on 2 legs. This is one of the defining characteristics of humans. But how did bipedalism develop, and why?
Bipedalism is such an unusual trait. There's no other mammal that habitually walks on 2 legs like we do.
Because it's unique, it's hard to figure out why it happened. There are a lot of theories.
One of them is that they stood up to be able to see over tall grass. Another theory, they stood up to be able to pick fruits off of the low branches of trees, the way chimpanzees do today. Another theory states that they stood up to cool more efficiently so that we don't have as much sun beating on so much of our body.
And I think the most compelling idea, the most compelling hypothesis is that it saved us energy.
And energy is crucial to survival. Let's go back to the dense forest, home to our ancient ape ancestors 10 million years ago. Like many apes today, they were perfectly suited to a life in the trees.
They're very good at climbing in trees. They're phenomenal at climbing in trees.
On the ground, these ancestral apes could probably walk on 2 legs for short distances if they had to carry something.
Fantastic climbers, but also able to walk and run rapidly and effectively, but not economically.
Walking was tiring, but they didn't have to walk far.
But if you're a chimp and you only walk 2 to 3 kilometers a day, it doesn't really mean much, right? It's not going to have that much of an effect on your energy budget.
But energy demands would change as the forest started to disappear. Our ape ancestors had to walk more.
They have to go farther to get from one fruit patch to another fruit patch, for example.
Dan Lieberman is an expert on bipedalism. He believes that walking on 2 legs evolved because it saved energy. When you compare the energy consumption of humans to chimps, there's no contest. A chimp is an energy glutton.
It spends an enormous amount of energy, about 4 times as much energy as a human walking.
Whether it walks on 4 legs or 2, a chimp can't compete with the human gait.
it's poorly designed to withstand the forces of gravity. It has to spend a lot of muscular effort to keep itself from collapsing into a little pile of chimpness or whatever with each step.
According to Lieberman, small anatomical differences created large energy savings, setting our ancestors on the path to bipedalism, a path that would eventually lead to us. But how long did it take? When Lucy's kind were first discovered, many people thought they were the so-called missing link between apes and humans. But the science of genetics has transformed our understanding with a technique called the molecular clock. Today, scientists can compare DNA from closely related species to find out how long ago they split from a common ancestor.
It's just a very simple idea that the rate of change in DNA sequences is more or less constant over time. And that's an extraordinarily powerful concept because it means that you have a way of determining when two species last shared a common ancestor.
Living forms evolve because DNA sometimes spontaneously changes as it copies itself. These changes happen at a surprisingly regular rate. By counting the differences between the genetic code of chimps and humans, we can calculate how long they've been evolving away from each other.
The dates that one almost always gets are around 5 to 7 million years ago for when humans and chimpanzees last shared a common ancestor.
Here was proof that humans diverged from the apes much earlier than we thought, about 6 million years ago. It shows Lucy and Salam weren't one step removed from chimps, but many. They may even be closer to us than to the first human ancestor. So what came before Lucy and Salam? Who was our earliest ancestor? Until the 1990s, the fossil record was blank. Fossil hunters combed East Africa's Great Rift Valley, but could only find small fragments older than 4 million years. Then, in 1997, a French anthropologist called Michel Brunet decided to look somewhere else.
We decided to go to Africa, but to the west. To the west of the Great Rift.
1,600 miles to the west, at the edge of the Sahara Desert in northern Chad.
Obviously, if you only go to the field in East Africa, then you are going to find fossils only in East Africa. This was the situation.
Michel was looking in a place where the few animal fossils he turned up were all around 6 million years old. No one expected any human-like fossils to be found in a layer that ancient.
And everyone said, no, there just aren't any fossils there.
Michel was not to be deterred. He was stubborn, many thought to the point of madness. He and his team spent years searching the desert for signs of our ancestors, and year after year, they came up empty. Then, on their 26th expedition in 2001, they found a smashed, misshapen skull around 6 million years old. They called it Sahelanthropus chidensis. There were no bones apart from the skull. Could it be a human ancestor or just another ape? The skull was so deformed, it was difficult to tell. Michel would have to reconstruct it. His first step was to take the skull, now nicknamed Toumai, to a particle accelerator in Grenoble, France, to use its powerful X-ray scanner. Over 1,000 pictures of the fossil were taken to build a 3D image of the crushed skull. Using the virtual image, the skull could be restored to its original shape. It was then reproduced by a type of 3D printer equipped with lasers which hardened plastic. When it finally rose from its bath, the cast of Toumai's skull was ready for detailed study. The cast allows Michel to answer an important question. Did this ancient creature walk on 2 legs millions of years before Lucy or Salam? It's how the skull connects to the spine that provides the vital clue. And Michel could infer that from the shape of Toumai's skull. If Toumai's skull is set on the neck of an ape that walks on all 4s, his eyes point downward. That can't be right. Set on the upright spine of a biped, his eyes point straight ahead. For Michel, this proved Toumai walked upright.
Anatomically speaking, he had a receding back skull of a biped. The back of his skull is not that of a gorilla, like some people are trying to say. No, not at all. All you have to do is look.
Some scientists still question whether Toumai was really a biped. But if Michel is right, his 6-million-year-old fossil is a good candidate for the first human ancestor. Discoveries like this are changing the way we see human evolution. Scientists used to have a simple idea. The growth of open grasslands forced our ancestors out of the trees. They became bipeds, and in short order, brain size increased. Human evolution took off. We were on our way to becoming human. That simple idea prevailed for more than a century.
Darwin thought that we left the trees, walked on the ground upright, freed our hands, made tools, got big brains, reduced our canines, and so on, all at the same time.
But walking upright may not have automatically led to big brains at all. From Toumai to Salam, both bipeds, brains stayed small. And they weren't the only ones. Over millions of years, there was a profusion of upright walkers with complicated names and chimp-sized brains. Like Auroran tuganensis.
What we're seeing is a fluorescence of species, multiple species. They're probably subtly different from each other.
Ardipithecus ramidus.
But it's important to recognize that there are not major differences among these species.
Australopithecus africanus.
They were all bipeds, big snouts, more or less chimp-sized brains.
Kenyanthropus platyops.
This way of life, this suite of adaptations, lasted for millions of years.
Small-brained bipedal apes were extremely successful. Debates rage among scientists about which one eventually led to us. But as a group, they flourished for about 25 times longer than we've been around. They survived and thrived as brain size flatlined for almost 4 million years. But that doesn't mean nothing changed. There's evidence that the seeds of our humanity were growing in these ape-like creatures. One key difference between humans and apes is the length of childhood. But what do we know about the childhood of our early ancestors?
We know all about the adult individuals, but we didn't know much about the children.
The brains of baby chimps have an early growth spurt. They're almost fully formed by age 3. In humans, that growth spurt is slower, and it takes nearly 2 decades for our brains to fully mature. But what about Salam's brain 3.3 million years ago?
That, of course, most exciting.
Her skull tells us all we need to know. We have her milk teeth and her adult teeth, which give us her age, 3 years old. And we have a cast of the inside of her skull, which tells us about her brain.
When you have this, you can directly measure how much of the brain was formed at age 3.
From other fossils, we know how large Salam's brain would have been as an adult. So Zerai could calculate how much of her brain was already formed by age 3 when she died. He knows what the answer would be for a chimp.
By age 3, a chimpanzee would have over 90% of the brain formed.
But Salam's brain was only around 75% of its adult size, suggesting it was growing up slower. Childhood would have been her time to learn the survival strategies her family group needed to live in a dangerous world. Perhaps this set the stage for our longer human childhood when culture is handed down. But is there any other evidence Salam's brain was becoming more human and less ape? To find out, compare a human brain to a chimp's.
This is the brain of our closest relative, the chimpanzee brain. Slightly larger than you would expect of a typical primate for their body size, not greatly so.
Scientists look for clues to the evolution of the brain in the folds and furrows on its surface. One important structure is called the lunate sulcus.
In chimpanzees, as in many primates, there's this big, deep sulcus here, the lunate sulcus.
The lunate sulcus is a deep furrow in a primate's brain. It divides parts of the brain related to vision from the rest of the neocortex, which is where more complex thought happens. The human brain doesn't have this deep furrow, and the neocortex is bigger than the vision structures, which have moved far to the back. So did Salam have the deep furrow and small neocortex of a chimp, or had something changed? Brains don't fossilize, but her remarkably complete skull provides a way to see some of the different structures of her brain. A cast of the brain case, called an endocast, preserves the impression of the brain's surface. Ralph Holloway has a collection of 300 brain endocasts from many of our ancestors.
What a paleoneurologist like myself will be looking for are those indications on the endocast that might suggest reorganization taking place. And that's why things like the so-called infamous lunate sulcus becomes important.
Ralph claims that as chimp-like ancestors evolved into creatures like Salam and Lucy, the lunate sulcus, the furrow marking the vision structures, moved back, making room for a larger neocortex, the thinking part of the brain.
If you look carefully, what you've got here is a depression that could very likely be the lunate sulcus. And so that suggests then by Australopithecine times that you're having a beast that is simply smarter than present-day chimpanzees.
If that's the case, although still the size of a chimp's, Salam's brain had been rewired. But there was a long way to go. She and her kind were still very ape-like. It would take another 1,000,000 years for the seeds of humanity contained in Salam's tiny frame to bear fruit. It's a time still shrouded in mystery. For almost 500,000 years, the fossil record is virtually silent. But in this blank period, something is happening. In 2.5-million-year-old layers, scientists begin to find something new. We might be tempted to call them rocks, but someone was shaping them. They are the first stone tools.
The way we know this is a tool instead of just a broken rock is that it's broken in a very particular way, breaking a flake off this way, this way, back and forth. So there is a method behind how this rock was broken in order to make it into a tool, and it's not a random method.
It's considered unlikely they were made by Australopithecus, Lucy's kind.
Australopithecus was around for a couple of million years and did not make stone tools.
But if not Lucy's kind, then who? The gap in the fossil record makes it difficult to say. But that's not surprising. Tools preserve easily. Bones, much less so. Finally, the skulls of a new creature begin to turn up. Is this the toolmaker? The skulls are different from what came before. They represent the dawn of a new era, beginning around 2 million years ago. This is our era, the era of the genus Homo, humans. The mysterious toolmaker, Homo habilis, is the first of these new creatures.
But we definitely have evidence that the stone tools were being used to break the long bones in order to get to the marrow inside the long bones. There were clear cut marks on the bones of turtles, crocodiles, big antelopes, little antelopes, even hippos, really big animals like hippos. So we know that meat had become a new important part of the diet of Homo habilis.
The first fossil to be called Homo habilis included 21 bones of the hand and was nicknamed Handyman.
This little bone is the bone at the end of the thumb. And that little bone in Homo habilis, like in humans, is very broad. And the broad bone reflects having a broad pad on the thumb with a lot of surface area for fine precision grip.
With newly dexterous hands, this creature could make better tools. But what was it like? The few skeletal bones that have been found indicate a creature much smaller than us, about the same size as Lucy and Salam's kind, Australopithecus, 3 to 4 feet tall. Homo habilis was still ape-like in many ways, but with a critical difference.
What we see in the evolution of Homo habilis is an expansion in the brain size compared to Australopithecus. So here is the skull of Australopithecus, and it has no forehead. It just has a straight slope behind the orbits. Whereas here in Homo habilis, you see a sloping, elevated forehead. And in Australopithecus, the area behind the orbits is pinched in, also reflecting a small frontal region. In contrast, in Homo habilis, we see an expansion of that area behind the orbits that points to an expansion in the cognitive capabilities of higher functions, of higher reasoning functions of the brain.
It was an expansion equivalent to a doubling of brain volume.
Once you go from something like 400 cc's in Australopithecines to, say, 700, 800 cc's in Homo habilis, yes, you're getting a big increase in cognitive capacity.
And along with his bigger brain, Homo habilis was starting to look a lot more human. The contours of fossil skulls allow reconstructionist Victor Dieck to reveal the faces of early human beings. Gone is the projecting snout of an ape. In Homo habilis, the face of humanity is emerging. This poses a great enigma. Why, after millions of years of flatlining, did brain size and mental capacities suddenly take off? Two million years ago, what jump-started human evolution? Scientists all over Africa looked for clues. Here in Kenya, they found some. At the southern end of the Great Rift Valley. It's a hotbed of tectonic activity where ancient layers are forced to the surface. 10 million years ago, Africa was a much wetter place. A tropical jungle which has been slowly drying out ever since. But these rocks in Kenya show that Africa's gradual drying trend was punctuated by bursts of wild climate fluctuation. Rick Potts is an expert in reading the rocks.
This layer right here represents about 1,000 years of environmental stability, but then we had an abrupt volcanic eruption, and then the lake was around for perhaps 500 years before a drought, and the lake came back. So in some cases, we saw this through layer after layer of environmental change.
With his trained eye, Rick could see some layers were once lake beds, others desert sands. Still others came from volcanic eruptions, a snapshot of 1 million years of climate history. This observation led him to an amazing new idea. Rapid change as a catalyst for our evolution.
And I began to think that, well, maybe it's not the particular environment of a savanna that was important, but the tendency of the environment to change.
Could it be that the need to survive violent swings of climate made our ancestors more adaptable? A group of scientists has come here from Germany to find out just how radical these swings of climate really were. It's hard to believe, but these huge rock formations are made of the shells of tiny one-celled organisms called diatoms. There are many different kinds, but they all live in water. Their shells collect in layers of rock that pile up over millions of years, proving that this whole valley was once a giant lake. Annette Junginger analyzes these rock samples under the microscope.
What I've discovered was that those white layers consist of a special kind of diatoms which only live in deep lakes.
But between the white layers, she also finds other species of diatoms which only live in shallow water. It means that in this spot, a massive lake appeared and disappeared and reappeared many times.
These lakes are really significant. These are not small little ponds. And what we've been able to document now is a series of lakes that are cycling.
When we're talking freshwater lakes, the size of Lake Victoria, filling the whole Rift Valley and then disappearing.
An enormous amount of water rushing through this area.
This constant flux of turnover, of change.
An awful time to live here.
It's not just a unidirectional change, it's going back and forth.
Against the backdrop of a slow drying trend, Africa was periodically pulsing with climate change. Wet, dry, then wet again, sometimes in the space of 1,000 years. Punishing drought alternated with storms and monsoons. Rivers and forests sprang up, then turned to dry grassland, all in the evolutionary blink of an eye.
So we have a complete change of our ideas, from this slow drying out to this incredible change between wet and dry, wet and dry.
What effect did that have on our ancestors? Could these periods of climate instability be the key to understanding the evolutionary leap from small bipedal apes to the larger-brained toolmaker, Homo habilis? To know that, scientists needed a detailed record that went back further than the diatoms, way back to the time when Homo habilis was evolving 2 million years ago. That's only found in one place, under the ocean. Layers of deep-sea sediment tell a story that goes back millions of years. They have to be drilled from the ocean floor. At his laboratory in upstate New York, Peter Domenico keeps thousands of columns of sand, silt, and rock, a library of ocean cores.
One of the really attractive features about ocean sediments is that they accumulate very slowly, but very gradually and continuously over time.
Each 3-foot-long core holds a continuous record of dust carried on the wind from Africa into the ocean, where it now sits on the bottom.
There we go, nice! There you go. Wow, sweet, okay.
An expert eye can detect distinct layers, thick in dry years when the dust is easily picked up by the wind, thin in wet years. By measuring the layers, they can tell when the climate was wet or dry.
So we can read these deep-sea sediments almost like an Earth history book of past changes in climate.
To make sense of all this dirt, they have to know when it blew into the ocean. They can do this by dating the shells of tiny sea creatures that sank to the bottom at the same time.
So this gives us an age, the other analysis gives us the climate. There we go, nice!
Peter took this finely detailed climate diary and compared it to the grand arc of our human evolution. For the 3 million years between Toumai and Salam, when brain size was flatlining, African climate was stable, dry, getting a little drier. Then came 200,000 years of wildly varying climate, careening unpredictably between wet and dry. During that time, stone tools appeared, along with the larger-brained creatures that made them. Africa was also home to many other human-like species. Climate instability put pressure on all of them.
So there are these time periods when African climate was really unstable. So anything that was living there at the time would have had to adapt to really dramatically different climate changes.
Those that couldn't adapt died out, like Salam and Lucy's kind. Better problem solvers, like Homo habilis, survived. The new discoveries about ancient climate upheavals in Africa have led Rick Potts to formulate a bold theory of human evolution.
The traditional idea we have had about human evolution is that it was the savanna, the grassy plain with some trees on it, that was the driving force. But instead, what we've discovered is that climate changed all the time. And so the idea that we've come up with is that variability itself was the driving force of human evolution, and that our ancestors were adapted to change itself.
It's a simple but revolutionary idea. Human evolution is nature's experiment with versatility. We're not adapted to any one environment or climate, but to many. We are creatures of climate change.
I think we should actually look to our proud ancestry and how we evolved in East Africa and say, that's how we survived that, we can survive the future. because we are that creature, because we are that smart.
Today, climate change seems to threaten our survival. But it may have held the keys to the astonishing story of how we became who we are. Because it didn't stop 2 million years ago. These dramatic upheavals would continue for another 1.5 million years, propelling our ancestors down a road leading ultimately to the smartest creature the world has ever known.
Nova's got a brand new evolution website with lots to explore about our ancestors. We want to know what you think. Bookmark it today and give us your feedback. Find it at pbs.org.